for indefinite integrals and the net change theorem. So here we have our fundamental theorem of calculus, which we've already discussed. And because of the relationship between the antiderivatives and integrals given by the fundamental theorem, the notation of the integral of f of x dx is traditionally used when the antiderivative of fn is called an indefinite integral. Thus, the integral of f of x dx equals capital F of x means that capital F prime of x equals just our regular notation f of x. We've discussed that in 5.3. So for example, we can write the integral of x squared dx is equal to x cubed over 3 plus c, because the derivative of x cubed over 3 plus c is equal to x squared. Remember, capital C is a constant and the derivative of a constant is 0. So we can rearrange an indefinite integral as representing an entire family of functions, one antiderivative for each value of the constant c. You should distinguish carefully between the definite and indefinite integrals. A definite integral has lower bounds a and b of f of x dx is a number, whereas an indefinite integral, there's no bounds, lower or upper bound, of f of x dx is a function or family of functions. And I think we talked about that before, where we said we could have, remember, plus 100 minus 1,000 to our integral, indefinite integral, I should say. If f is a continuous function on a to b and closed interval from a to b, then we know that if we integrate our function, we're going to be evaluating that from b to a. So this new notation here that we're seeing, that tells us how we're evaluating it. Enter this value first, then that value. All right, indefinite integrals. So we looked at some of these just to rerun this through again one more time. If you have a c times integral, remember you can factor that to the front. If you're adding or subtracting, same thing. We can add or subtract the two integrals separately. If we integrate a constant k, that's going to be kx plus a c. X to the n dx, that was our power rule. Add 1 to the power, divide by the new power to the function, plus c. Remember that your power cannot be negative 1. That's reserved for the one to the right here. Integrate 1 over x, we found that to be the natural log of absolute value of x, and again, plus c. And integrate e to the x dx. Remember, that's just e to the x. It doesn't change, so plus c. b to the x dx, that's going to be b to the x divided by the natural log of b plus c. If you're confused on how that one works, then please ask about that one when we have class, and we'll go through it on the board. Sine of x dx was our negative cosine x plus c. Integrate cosine of x dx, that's our sine of x plus c. Secant squared x dx, if we integrate that, that was our tangent of x plus c. Integrate cosecant squared x dx, that was our negative cotangent of x plus c. If we integrate secant x times tangent x dx, remember that's the derivative of secant x. And cosecant x cotangent x dx, that's the derivative of our negative cosecant x plus c. And then we have our two special cases. Remember these fractions. We got the inverse tangent here. So 1 over x squared plus 1 is the derivative of the inverse tangent of x. And 1 over the square root of 1 minus x squared, that's our inverse sine of x. And again, plus c's on both. So find the general indefinite integral of 10x to the fourth minus 2 secant squared x dx. So notice that if you wanted to, you could write this as two separate integrals, or we can just integrate each one. So 10 times, let's see, add 1 to the 4 is 5, divide by 5, that gives me x to the fifth over 5. You can cancel 5 into the 10 right away and call it 2x to the fifth. Minus 2 times, let's see, if we integrate secant squared of x, we said previously that's tangent of x. And so there's our final answer, 2x to the fifth minus 2 tangent of x plus c. Evaluate cosine theta over sine squared theta d theta. Again, I think we saw this before. We want to separate this. cosine theta over sine theta. I think the last time we had it was sine theta over cosine squared theta. So this is going to give us cosine theta over sine theta is cotangent theta. 1 over sine theta is cosecant theta d theta. And that's going to be our negative cosecant theta plus c. Example 3. Now, this is a definite, so we got values here. I think this is one we did earlier. We would integrate x to the third as x to the fourth over 4 minus 6x squared over 2. We could simplify that to minus 3x squared. We substituted in the 3's. So 3 to the fourth over 4 minus 3, like I said, 6 divided by 2 is 3. 3 times 3 squared. Remember, the 0 is just going to cancel everybody out. So that was 81 over 4 minus 27. I think we did this example before, which we said was a negative 6.75. Example 4. Let's find this definite integral. You should recognize that last fraction with the denominator, x squared plus 1. So what we're going to do is we are going to factor that 3 off the top. So it's 1 over x squared plus 1. So we integrate 2x to the third. That'll be x to the fourth over 4. With 2 on the top, we can reduce that. Here we're going to get x squared over 2. We can reduce the 6 and the 2. And we factor the 3 out front. So that's 3 times the inverse tangent of x. And now we'll evaluate it from 2 to 0. So 2 to the fourth, remember we reduced to 2 fourths. 2 to the fourth over 2 minus 3 times 2 squared plus 3 times the inverse tangent of 2. Then minus zeros for the first 2 terms. And then we got to check that 3 times the inverse tangent of 0. So to my calculator I go. Inverse tangent, 3 times the inverse tangent of 2 is 3.321446153. And then the inverse tangent of 0 is 0, so that whole thing is just minus 0 on the right. We don't need that anymore. But we're going to have to take that decimal value. We're going to have 16 over 2, or 8, minus 12, plus that 3.3214. We're going to have to enter that in the calculator, and it comes out to be negative 0.6786. So again, that's interpreting that more area is below the x-axis than above the x-axis. All right, as we said, the area below the curve has sections below and above the x-axis. There'll be more area below the x-axis than above the x-axis. Example 5, evaluate from 1 to 9 our integral of 2t squared plus t squared, times the square root of t. We're going to have to separate this up, put t squared underneath each one. Then the next thing I'm going to do is I'm going to change this square root of t to the 1/2, so I can add those two together, or we can cancel these right now and call it t to the 1/2. So 2 plus t to the 1/2 minus t to the negative 2 power. Integrate that, we'll get 2t plus 1, that's 3/2, so 2/3 t to the 3/2. Plus 1's negative 1, so divide by negative 1, so minus this negative is going to cancel out to a plus. So when we evaluate and plug in the 9's, we might want to change that to a plus. So 2 times 9, then 2 times, so t to the 3/2 is really the square root of 9, or the square root of t, then cubed. And I'm going to take the square root of 9 first, which is 3, and then I can cube it over 3. And then my t to the negative 1 is just 1 over t, so that's 1 over 9 for my first value of 9 I plugged in. Then we're going to substitute in the 1. Every place you see the 9's here, we're going to put in a 1. So let's crunch the numbers. We'll have 18. Then let's see, 3, square root of 9 is 3. 3 to the third is 27. Or 27 divided by 3 is 9. 2 times 9, that's another 18. Plus a 9, so that's 18 plus 18 plus a 9th. Here we got 2 plus 2/3 plus 1. So crunching this all out, 36 and 1/9 minus 3 and 2/3. I opted to change it to 6/9, so I had common denominators. So 36 minus 3 is 33. 1 minus 6 is negative 5. So I'd have to borrow from the 33 to make it 32. So that makes it 32 4/9. All right, so there's part 1. We'll come back with part 2. Oh, you know what? Let's just go for it and get it all done. This is going to be rather quick here. Applications of our theorems here. So just remember our definition, part 2. So from a to b of f prime of f of x dx, f prime of x dx is capital F of b minus f of a. And again, we know that capital F prime of x represents the rate of change of y equals capital F of x with respect to x. And capital F of b minus capital F of a is the change in y when the x is changed from a to b. Note that the y could, for instance, increase, decrease, and increase again. All depends on what's going to happen in between from a to b. All right, so capital F of b minus capital F of a represents net change in y. It takes into consideration all the positive areas, negative areas, and maybe back to positive areas. The net change. Sometimes we call that displacement. So the net change theorem, the integral of a rate of change is the net change, again, what we've done before. So it's the same thing. It's, again, if you will, part 2 of the fundamental theorem of calculus. This principle can be applied to all of the rates of change in the natural and social sciences. Here are a few instances of this idea. I'm not going to spend too much time on this. Just go ahead and pause on each one and fill it in. So V of t is the volume of water in a reservoir at time t, when its derivative v prime of t is the rate at which water flows into the reservoir at time t. Now, if it's a negative, that means it's coming out of the reservoir. So if we wanted to write our integral from time 1 to time 2, v prime of t dt is equal to capital V of t2 minus v of t1, is the change of the amount of water in the reservoir between those two times. If capital C of t is the concentration of the product of a chemical reaction at t, then the rate of the reaction is the derivative of that capital C of dt. So again, rewriting this as part 2 of our fundamental theorem of calculus, here's your change in the concentration of C from time of t1 to t2. The mass of a rod measured from left end to a point x is m of x, and the linear density is rho of x equals m prime of x. Therefore, we can integrate from a to b rho of x dx equals m of b minus m of a. Is the mass of the segment of the rod that lies between a and b. Rate of growth of a population, same type of setup. You just have to use the appropriate names. If C is the cost of producing X units of a commodity, then the marginal cost is the derivative, C prime of X. So, again, integrate from T1 to T2, C prime of T dt gives you capital C of T2 minus C of T1 is the increase in cost when production is increased from X1 units to X2 units. Object moves along a straight line. Oh, here's our favorite position function. The velocity v of t is s prime of t, so if we integrate from t1 to t2 of the velocity function with respect to dt, then the position functions s of t2 minus s of t1 is our net change. Or, there it is, displacement. Net change of a position is displacement, also known as your net change. So this is true for the case where the object moves in the positive direction, but we have proved that it is always true. If we want to calculate the distance, this is different now. The distance has to be a positive value. The distance the object travels during the time interval, we have to consider the intervals when v of t is greater than 0, say moving to the right, and also the intervals when v of t is less than or equal to 0, which is moving to the left. In both cases, the distance is computed by integrating the absolute value of v of t, the speed. All right, so it's got to be the absolute value. If you integrate from t1 to t2 of the absolute value of v of t dt, that's total distance traveled. You have to keep the absolute value bars there. All right, so Here's an example. The figure below shows how both displacement and distance traveled can be interpreted in terms of areas under a velocity curve. So here's my curve made up of three different areas, A1, A2, A3, and obviously A sub 2 is below the x-axis, therefore it's negative. So its displacement would be just to add those three together. So A1 plus the negative, which would be minus A sub 2, plus the positive A sub 3, that would be your displacement if you integrated from T1 to T2 of V of t dt. But if you're looking for distance, then everything here has to be positive. It would be positive A1 plus positive A2, so you're taking the absolute value of each part of the area, so they're all positives. So that's the total distance traveled. That's the key. So make sure you understand the difference between displacement, net change, and distance. Everything's positive. The acceleration of the object is a of t equals v prime of t, so we can integrate from t1 to t2 of our acceleration function a of t dt, which equals the velocity functions v of t sub 2 minus v of t sub 1 is the change in velocity from t1 to t2. All right, example 6. A particle moves along a line so that the velocity at time t is v of t equals t squared minus t minus 6 measured in meters per second. Find the displacement of the particle during the time period from 1 to 4. It's bracketed, so it's closed interval, so we can write this, we'll integrate it from 1 to 4 of t squared minus t minus 6 dt. There we go. Now again, remember, to the left is negative, to the right is positive. So we're looking for displacement here, our net change. So we integrate that, so that's going to be t cubed over 3 minus t squared over 2 minus 6t. We substitute in the 4 for all the t's, minus, substitute in the 1 for all the t's, and evaluate each one of these separately. So we're going to get 64, 4 to the third is 64 over 3 minus 16 over 2, which is minus 8 minus 24. Minus, our next value would be 1/3 minus 1/2 minus 6. So crunching the numbers, we get a negative 32 over 3 for the first evaluation of t is 4. T of 1, we plug that all in, we get negative 37 over 6. But minus a negative makes that a plus, so we get a total of negative 9 over 2. So the displacement means net change, that no matter how much we went to the left or to the right, at the very end, we ended over here to the left of where we started. That's what our displacement. The particle displaced 4.5 meters to the left. When all is said is done, it's 4.5 meters to the left of, if you will, the starting position. Part B, find the distance traveled during this time period. Okay, now what we're going to have to do is we got to figure out where did we stop. So we may have gone to the left first, then to the right, or maybe we went to the right first, then to the left. We have to find where is our stopping point. So first we need to determine where the particle stops and changes direction. So this is when v of t is greater than 0 is positive. That's when it's going to the right. And when is v of t less than 0? Negative. So we take our t squared minus t minus 6, set it equal to 0. Remember, this is the velocity. This is like saying the first derivative, or the s prime of t, the first derivative of your position function. So we factor that, we solve it, we get t equals 3 and t equals negative 2. But remember, we were working between 1 and 4, so t equals negative 2 is not in our interval of time. So 3 is the key here. So again, we have a positive t squared, so your right-hand behavior is positive, left hand is negative. So this is when to the left of 3, so from 1 to 3, we must be going to the left, and then from 3 to 4, we go to the right. Okay? All right, so second, well, let's integrate our intervals traveling to the left, so that's going to be 1 to 3. So we're going to integrate from 1 to 3, t squared minus t minus 6, all inside of absolute value bars. Again, because it's distance, we need to have a positive answer, dt, plus then we're going to integrate from 3 to 4. Well, since we know we're going to the right, that's going to be positive. We don't need absolute value bars. If you wanted to, you could put absolute value bars around both. That's fine. Just make sure these both come out to be positive. All right, now when we integrate this, remember these two are going to be the same answer. So that's t to the third over 3 minus t squared over 2 minus 6t in absolute value bars, evaluated from 1 to 3. And then this is the same, t to the third over 3 minus t squared over 2 minus 6t, evaluated from 4 to 3. Remember, you're going to plug in 3 twice, so let's not double the work. Once you have this answer, hang on to it. We're going to need it for over here. So I plug in that 3 into all my t's, minus, then plug in all my 1's. So this answer from my first big binomial here, I'm going to be using that twice. So we want to find that, make sure it's right, because you got to use it again twice. So we're going to crunch those numbers out. Then we're going to add to that, plug in the same formula with the 4 and the 3. So here, like I said, the first trinomial and last trinomial are the same. So this is 27 over 3, which is 9. Come on, mouse. Minus 9 over 2, minus 18. So I crunch that out. It's a negative 13.5. I'm going to use that over here. This is going to be minus 1/3, minus 1/2, minus 6, which is negative 37 over 6. So minus a negative is going to change that to a positive. Here we're going to get our 4 to the third, which is going to be, let's see, 4 times 4 is going to be 16, is 64 over 3, minus 16 over 2. Let's just go punch in the calculator. That's what we did, negative 32 over 3. And like I said, we don't have to evaluate that one. We already done that. So now we're going to crunch out all the numbers, negative 13.5 plus 37 over 6. And absolute value bars plus, in parentheses, negative 32 over 3 minus a negative, which would change that to a plus. So if you want to put in a plus, that's fine. 13.5, close the parentheses. That gives us a total distance of 10.16 repeating. So 10.167, if we round up to 3 decimal places, that's total meters traveled. All right, that ends this section.